Hello friends, welcome back to my YouTube channel Infinite Knowledge, and I am back with another great MATLAB project. I have recently uploaded one video which is IEEE 14 bus system, and you have given enormous support over this video. What I have done the load flow analysis with the IEEE bus in that video. So I have just updated that model. So this is the model that I have explained in that video, and in which you can see it's a 14 bus system, and which is connected through the 415 volt. Even though we are generating 11, we have connect the system with the 415 volt, so all the buses are on the 415 volt, and we are getting this voltage, and this is a per phase voltage. That's why it's not a per phase, it's a phase to ground voltage, and that's why it's a 245. Okay, and here we are measuring for this specific bus. So just concern is there कि whenever the substation is there, or whenever you are connected the substation with the substation or state to state connection, we are mostly going with the higher voltage. And for checking the load flow analysis, doing the load flow analysis for that much higher voltage, I have redesigned this 14 bus system with the 220 kV. So yes, you can see here we have used a generator. Obviously all the generators are working on the 11 kV mostly, and that's why I have considered the 11 kV. Here I have generated the 11 kV and step up with the step up transformer to the 220 kV. So here it's a 14 bus system in which all the buses are on the 220 kV or 220 kV. Okay, so why I have used this voltage? Because if you go through this power grid map or power map of India, you can see here most substations which are connected to each other, state to state connection, means Gujarat to Maharashtra or Punjab to Haryana, which mostly with the higher voltage level, higher voltage 765 lines. So all the lines which is red highlighted are the 765 lines. All the line are the blue highlighted is the 400 kV substation. So these are the existing. Okay, and if you go to the power map of the Gujarat, specifically Gujarat, then you can see most 220 kV substations are highlighted with the green lines. So most substations are the 220 kV which are connected to the different state, like this to Nasik, Maharashtra. So mostly when you are connected, even for the small area or even state to state, you are connected through high voltage like a 220, like a 400, like a 765, and that's why I have used 765 voltage. If you want this power map, you can just write power map of India, power map of Gujarat over the Google, and you will get this map, you will get this graph. So yes, we are back to our video, and this is the latest model in which we are going with the 220. So I just run the simulation. Yes, in this model there is one swing generator, and I think one, two, three, and one at the bottom side. Four are the PV generators. Okay, this is the PQ generators. So as you are aware about it, the PV and the PQ, what is the difference of the swing? Swing is main substation, or I can say not a substation. Swing is treated as a grid. So all the generator will try to follow the voltage and frequency of the swing. This is the main reference, I can say. It is a grid, one type of entire grid which has some frequency, and all the generators which are connected in the power plant try to maintain that frequency, try to maintain the level of that frequency and the voltage. So these are the PV generators. PV generators are used to provide the reactive power to the system, and the PQ generator are the generator which has some specific capacity, and according to this capacity it is providing the power. No matter what is load, it is just providing this much amount of power to the system. There is no any control. Whereas the swing bus is control active and reactive power. If the reactive power increase, swing bus take extra reactive power, and if it is reduced, it give extra reactive power to the system. Same for the active power. If the power is higher, active power is higher in the system. Why it is higher? Due to these generators, it will take extra power, and if it is lower, then it will feed. So it is one type of control. It can feed or it can take as per the requirement of the system. And yes, if you want the load flow analysis, I just run the simulation and you can see there is some voltages are coming over here. So this is the, again it is a voltage which is phase to ground voltage, and if you multiply 1.278 into 10 raised to 5 into 1.73, then you will get 220 nearly. So if you want, we can do that. So what it was, sorry, sorry, 1.278 into 10 raised to 5. Okay, this was the value. I have to multiply it with the root 3, or you can say 1.73. You are getting 220, 221, nearly this value we are getting. Okay. So if we want the load flow analysis, or if you want the waveforms also, you can see these are the waveforms, and you can see it's a very clear sine wave. You can zoom the waveform as per your requirement. Okay. So waveforms are very clear. It's a three-phase waveforms, and I can say, so yes, voltages are also same because bus are totally connected. So if you want to do the load flow analysis, just double click on this discrete block, go to tools, check these parameters. So sometimes you are getting the iteration error. So if you are getting, just increase this value and just press the load flow analysis. After some times the pop-up will open for the load flow analysis, which takes some time. So you can see all the buses are mentioned over here. There is a swing generator, there is a 3 PV generator, and one is a PQ generator. And yes, you can see different voltage level. All the generators are 11 kV, and all the load are for the 220. Whereas if you want, you can just press the compute. Once you press the compute, after some times you will get this amount of value. This is the voltage per unit, this is the angle, this is the power, and this is active power, and this is the reactive power. And load flow, after the load flow analysis, we will get this value. We need to wait for some time. So you can see we are getting the voltage active. Okay, if you want the proper value, you can check change into the kilowatt. So our generator, which is on the swing generator, is providing this much amount of kilowatt, and this is a reactive power. Remaining reactive power is provided by this PV generators. So if you reduce this value by just going to these blocks, you will get change in the load flow as well. And we are getting this 23, 24, 25, 26, 27 because it was by default considered. So we need to just correct it. I just correct it and I will upload. So okay, I have correct the name as per the bus name: bus 1, bus 1, bus 2, bus 2, bus 3, bus 3. And if you go back to the load flow analysis, you can see generator 1, bus 1, we are getting this much amount of active power from the generator 1, and this much amount of reactive power from generator 1. Same generator 2, we are getting the 20 kilowatt active power, and 1.1135 into 10 power 3, matlab 1.11 kilowatt. So these are the reactive power, not a kilowatt, because it's in the kilowatt. Okay, yes. this is the issue in the MATLAB. Even though you change the reactive megawatt, you can see values are changing, but this is the MVA and this is the megawatt. Now we are changed to the kilowatt kVAR. So yes, this is changed to kilowatt, but this is again in the MVA. This must be changed into kVA, and this is the value of kVA 1.1135 into 10 power 3 kVA, not a MVA. So make sure you are aware about it. And yes, if you want, like if I reduce this value, like the generator 2 is providing this much amount of reactive power, so I just go to the generator 2, and this is the reactive power that it is providing, and I just reduce it by these values and then check whether the values will change or not. So in the load flow analysis, I just go back to the load flow analysis. Initially, the generator 1 was a swing generator, and which is providing this much amount of reactive power, I can say 400, and generator 2. So right now I have reduced the reactive power of the generator 2. So that reduction in the power, reactive power, was taken by the swing generator. This value must be increased. So again I just compute. So 400 will be increased. I think we need to run the model again. Okay, yes, it is running. Okay, yes, the simulation is run is completed, and you can say the swing. The initially reactive power fed by the generator 1 swing generator was 400, is increased to the 465. So yes, this is how the system is working, providing the reactive power to the system, taking the extra reactive power from the system. So I can say our simulation is working very much clearly. And if you want the waveforms, you can check at any scope. Any scope I have added scope for every buses, and which is very clear sine wave at every stages. I can say this system is working satisfactory at the 220 kV. This is a step-up system in which we have these are different generators. These are located in the power station, and these are, you can say, this is not a load. It's one type of substations, 220 kV substation. These are the different substations, like 1, 2. All the loads are treated as a substation here. Okay, as per the graph that I have explained earlier, like this, these are different substations, and this is the stations, because all are on the 220 kV. So thank you for watching this video. If you have still any queries, comment it, I will definitely reply. And if you want this file, you can connect with me through my email ID that is given in the description box. If you want any modification in this system, I will do as per your requirement. And for any type of MATLAB project, electronics project, electrical project, you can connect with me through my email ID that is given in the description box. Thank you very much for watching this video, and don't forget to like and subscribe and press the bell icon. Thank you.